Welcome back to High Performance Computing, our lecture 3 on parallelization fundamentals. This is a part 2. Basically in part 1, we discussed several important terms. We try to have a general understanding of what it means to decompose a domain. And the domain can be many things. It could be basically a train that you set on fire and want to simulate the different materials in the train. It could be earth science simulations that we have seen, like numerical weather prediction. This is all a simulation domain, maybe a certain region where you want to have the weather forecast, or where you want to understand rain research, maybe with precipitation and so on. So the idea of a domain is, of course, a word which is very abstract, but in many cases it reflects what we want to simulate with basically known physical laws using numerical methods. Or as we also have seen, we can transfer this concept also to the data scientist. So there in the data sciences, we maybe have, let's say, this cluster algorithm that you have seen in the first part, where we basically have several points we want to cluster based, for instance, on the Euclidean distance. And then we have to have the whole data set basically as the domain. And in order to speed up this clustering, we can basically crunch this big domain into smaller pieces and then essentially cluster all of them on their own and then merge these basically later to larger clusters together. So hence this domain word is something which is basically an abstract term, and it really depends what is the application at hand. Also, we learned a little bit about this interesting technique called halo regions. This was important also in the light of this time loops that we have often in HPC. The time loops reflect usually time steps to really have a physical phenomena simulated over time. So we had the heat in the room or the race car driving. So whenever you compute this usually and compute the physics, maybe with partial differential approaches and equations and so on, then basically we have always time steps where we step after step compute the new status and then basically go one step ahead. But what we also learned, which is now the interesting thing where halo regions and ghost layers come in, sometimes I just can't do that when I, for instance, need in the next time step the heat in the room, we said, from all my neighbors, and suddenly my right neighbor is in the memory domain of the other processor, right? So we learned there, we basically do an halo exchange before the current time step in order to compute the time step now. And we need space for this, right? Basically, we introduce this artificial, let's say, domain parts, which are not really existing. That's why they call it ghost or halo layers, where I can store the variables to compute the physics properly in the current time step. And this is a very known approach, often in very many applications actually present. So now in the second part, we want to come back to some of these elements we discussed. Admittedly, we had some very simple examples and a couple of more advanced examples, but we here and there left out some important terms. And of course, when we talk about Speedup, there should be also a little bit, theoretical formulas, although we keep here the theory really to a digestible pieces. Don't worry about this. But we start a little bit by looking back again from high performance computing as a whole, why I want to do parallelization. I alluded to the train. You see that as an example here on the left. So obviously, this would be far too expensive to again and again burn the train with different materials maybe, and you'd have perhaps lots of different carriages to simulate. And basically, you can experiment with this doing HPC very nicely. You can burn the train many times. It doesn't cost anything, only energy, so to speak, of the HPC machine. And of course, we can do this with much more granularity, even more these days. But this also means more expensive computing. And with this, we are quickly at HPC, so we can parallelize the train simulation. We can parallelize all other elements and then make these calculations faster or even possible, right? Because burning a train in a very high granularity would be, of course, not really possible in a small laptop. Hence, this is something which really requires HPC, especially if you want, maybe as this picture suggests, more an interactive way, connected to a visualization actually, so that you can interact with the strain while burning and so on. So a very interesting approach of HPC, often combined with different areas of physics, or as we also learned with data sciences. And here HPC is always there at the forefront of computing. We also had already the NVIDIA Volta architecture. I play the video once more a little bit, but just so that you basically also grab the idea with the number of transistors, with Moore's law, sorry for this, always growing up, basically that we double every 2 years on the number of transistors on microchips. And some people say it's basically stopped, but some people say it's still carrying on, and especially if you now think about multi-core and many core areas, which are more recent. So let's look a little bit on the Volta architecture, although we will have a GPU lecture also. So here's the idea again. You see essentially here lots of this many core architecture parts in the video, but you also have seen how nicely this was reflected now again with Moore's law. Basically, we see there's of course more problems of putting more transistors on the chip, as I was alluding to in the multi-core setup, because it's just too hot. But the idea of the GPU by accelerators with the many cores is to make the chips basically not in the very high speed frequency, but just have very many of them. And this kind of helped, as you have seen in the video a little bit, with having still more basically computing power available every year. So basically, this is more something which is a term which is not necessarily only HPC, but Moore's law is often discussed in the area of HPC. And as it is alluding these days massively also to parallel computing, it's something you really should know by heart. And of course, today, the parallelization, let it be with multi-core processors or many core processors, is something which even normal laptops are basically engaging in more and more in all normal applications. Of course, we in the HPC domain seek very large scale parallelization techniques and large scale applications of HPC. But still, the key essence why you basically have this idea of parallelization is usually twofold. You would say basically a single core, or let's say a small laptop with a multi-core chip, is still too slow to perform the real required simulation task, right? So especially if you think about, you have a very constrained amount of time. Let's say you want to simulate avalanches for Flattery, when there's some, risk or alarm status, you don't want to wait for several months to compute all of that. So hence the time is a very important factor as well, where parallel computing comes in. In some points, you have seen the granularity in the first part. We would even say it's the other way around, where it's not necessarily just the computing, it's more the memory, which means we need lots of details, or the burning train, where you have lots of details in all the material properties, in all the physical formulas that you have to compute on it, on all the data that is required for this. We basically have a granularity which sometimes is so precise that basically a laptop cannot really simulate this as well. So there is not the speed necessarily, it's just also the memory, the whole domain, especially if you think about NWP, numerical weather prediction over a country, for instance, or so. This is something which is not for laptops. Hence, these are the two major reasons that you should also know by heart why people go for computing. Perhaps a speed up in the first place, it would be too slow otherwise. And the other one is just making it possible, even with having granularity, and the memory enables it, because you have, of course, much more aggregated memory when you use parallel resources, parallel HPC machines. And then basically the parallelization methods you already kind of have heard about the SPMD and the MPMD in the first part. So this also influences, of course, the methods that you use there. Coming more to the idea of the speed up term, this is, of course, a term which is often used, and we basically have the different graphs that you can use for it. And we will basically talk about this one by one. And these graphs will come again and again in this lecture when we have different applications, because obviously that's one of our main goals in parallelization. We want to speed up things. So similar like the array we had in the first part, where we said we have so many array elements, which were 16. We have here maybe different elements, which could be alluding here to time steps, that it's required in these 12 time steps to do a certain computation, right? And this would be when we have just one processor. So when we have here then these different workers instead, and could work on this problem in parallel if the application allows it, then we would basically say N is here 3 workers, right? So basically 1, 2, 3, they work over the time, and we see directly, instead of 12 divided by 3n, yeah, the time step it takes for 1 divided by n would be basically the ideal speed up, right? So we would say instead of 12 time steps, we just need 4 time steps. Very obvious, because we have 3 processors. So hence this would be a general speed up term. We try to have the overall time, of course, it takes divided by the number of workers, and hopefully you have more workers. And then you come to the kind of speed up gain, so to speak. So much for the more theoretical point of view. In theory, it's not directly what we observe in practice, however. So you see here what it usually looks like. And this is something which is a very important term as well in theory, that you basically have to learn in HPC theory, which is called load imbalance, which is not only a theoretical term, it's really practical, observed in many applications. And I will bring a couple of examples again and again. Here you see the, the initial idea of really using different workers sound good, because then you essentially say you have a speed up basically obtained by making it faster. But there you also have to be careful, because some resources might be underutilized if you do this. Because not at all is always each application problem so easy to be cut in different pieces at the same time it takes. You see quite here that these 2 processors, these 2 workers, actually earlier ready, but the whole job is waiting, of course, for the first worker to be finished. Hence, these resources are unused. And this is what we call load imbalance. This is, of course, on a larger scale, much more a problem than in this little toy problem here, but it should point to you to one of the big problems in parallelization. And this is something where administrators of the system are quite listening to your applications and looking if you really use the resources that are requested. Because for the scheduler, what you occupy here is actually 3 cores all the time, right? It's not that they will be suddenly giving for free away this time. They have to stick with the application. So the scheduler, in a way, if you want, sees it as a full block. There's no way that these 2 cores will be just given to another application, because the whole MPI application, for example, is not finished. And by having underutilized resources again and again, let's say in a very big MPI application, can basically lead that the administrators will call you and will say, you have to optimize your application, otherwise, you know, you're not allowed to use here so many thousand of cores, because in the end, these systems are very expensive, and you really have to make sure to optimize your application to use the resources to the full extent as best as possible. And there are different basically ways why that is happening. I give you some examples. Could be communication paradigm, could be master worker idea. Of course, still there are always room for improvement with parallel performance analysis tools and so forth. But this is a very important term, load imbalance. Be careful on this. It's easier actually programmed than you think. And I give you a good example on this, which you can allude to, I guess, from the first part. You remember we had the array. That is a very good example as well. We had the 16 array. We wanted the maximum. And then, yeah, well, that's an easy problem. So we have the 16 array, and then, basically we have 4 processors. Let's cut them all into 4 pieces, compute that locally for these 4 pieces, and then magically, and now that's the point, magically, there will be a global maximum computed. We also learned this magically is loaded. There is no magic in computing. One core has to do this, right? And this is a usual example of a master worker paradigm. Although you would say that all of them 4 are equal, they have the equal amount of data to do. They do the local, compute of the maximum, very easy. There's the first rank, for instance, like in the example here, that just has much more things to do because it would, for instance, also compute the maximum globally and basically collect first all the results, right? And these are one of these parallel performance issues where you have the master worker paradigm, which causes sometimes load imbalance, especially if you chunk up everything in the same pieces and the master has to work as well. So you see that a little bit in a sort of example here with MPI, with different ranks. By now, basically these are different processes within one parallel application, but you see not only is rank 0 here out of band, because basically what you see also is that this whole application, right, when you see the time in seconds, or let's say if that would be hours, it would be perhaps more a problem. Seconds is now okay. Anyway, a very interesting sort of problem. But for the scheduler, this is the whole block, right? The whole time will be scheduled on the HPC machine. Working is just 1, because they are all idle here, right? Nobody's doing anything. But already here, this kind of up and down between the different ranks suggests that basically all of them have very, let's say, parallel performance issues somehow. Plus, of course, rank 0, which is really out of band here. And there could be different reasons for this. Basically, some synchronizations which are not needed. There are sometimes the effect of this master, as I said, which is sort of introducing a serial limit, right? Because the master has to do things first, like collecting, let's say, all the communications to get all the, let's say, local results from all the other arrays. And then I have to compute my global. That's a serial idea because I can parallelize this. And then I stick with the serial part. And these are the issues that couldn't happen, which is this load imbalance. And we see this very often in these applications. And that's why parallel performance analysis helps you to understand exactly what we see right here on a more granular level, where I basically synchronization paradigms in MPI. We will learn this a little bit more in lecture 4 when we talk about advanced concepts of MPI. So waiting for others. Or basically you have this kind of master worker problem. I think it's pretty clear. So let's move ahead a little bit with ideas of how can be domain decompositions also different, right? And I think one of the interesting examples you see here is this idea of having more tree codes and why you won't be possibly interested in this. We see here basically an n-body simulation. N-body is a kind of problem, which means there's several different particles may be involved. Could be astrophysics, could be plasma physics. Here we see a laser gun, basically for treating cancer treatments and so on. So basically, what we want to be interested in is basically speeding up this. And of course, the physics is basically in all of these different particles that you see the same to be computed, the interactions. But when you think about that, you have some long-term interactions or long-range interactions, then basically sometimes it makes sense to treat all of them more or less similar, right? So instead of computing all of this very, in all in detail. So this is something where we can speed up, for instance, these particle interactions, which can be quite many particles. And with this, basically have the problem that this becomes more and more computationally expensive if you have more and more particles, and all particles have somehow basically to interact with each other. And tree codes here are just another example where you see sometimes you have the domain not just chopped out, as I said, in blocky domains, or basically as we've seen in the Cartesian grid structure or from the world in the earth science application, if you remember, with the grid, horizontal, and so on. So here we talk about much more interesting approach to make the parallelization and the physics behind it faster. And with this, we are much more in a tree structure. Although, of course, you could do the same and just divide it by 4 processors equally, but then you also see that perhaps one of the processors almost nothing to do, another one is far away from the core part, so you see load imbalance again on the way. Hence, there are really smart domain decompositions in these applications when you go to production. Not everything is always the same, and what we are always interested in is this so-called scalability. When we make things faster, we want to use, let's say, more and more of this n number of processors that we have available. And you see this tree code here, for instance, it scales to an old machine, BlueGQ, it doesn't matter, to the whole machine. So that is quite nice. And basically says that there are no limits, more or less, right? But this is not true, because many parts actually are affecting the scalability of the application, right? This is a HPC system. It has lots of system and network capabilities, where also the amount of work that you have basically in the application, which is more and more, needs to really scale with the system at hand. And although you achieve probably a speed up at some point in time by adding more and more cores, and here the whole machine, all nodes, the maximum if you want, you will be more and more limited. And there are 2 metrics which are important now to measure in that context, right? And this is called strong and weak scaling. So when you have some applications in HPC, especially in simulation sciences, physics, often you see these metrics, strong and weak scaling, which is basically reflecting to the idea now, how good is an application scalable? And of course, this means also related to the work of the workers or of all the cores. Is it really faster? What is faster? And so on. So there are different workloads we have to consider in order to make a problem faster if you want. Also, if you think the amount of work that you want to simulate to keep it constant, or basically grow with the number of processors available. Hence, these words are all loaded, and usually also in the exam, I know from experience that some people have still issues understanding this. So I put you some green helper elements again in. But when you think about Speedup, that's very intuitive, right? We have number of cores, more and more to add to a problem. Let's say here is basically our clustering algorithm. We have an MPI version on dataset 1. You see basically it scales quite nicely. You see often the linear scaling, which is of course the optimal perfect scaling, which you often cannot really achieve. You will find papers that talk about near linear scaling, like here you see the hybrid dataset 1. You would argue it's maybe near linear scaling, but often you see at some point in time there will be tail-offs, like here, right? And this is not even on a logarithmic scale. Sometimes these graphs have also logarithmic scales. I keep it here very simple to always understand the speed up in parallel. You put more number of cores. You suggest that basically speed up should be quicker and quicker. But as you see, basically the limits kick in at some point in time. And so we have to talk about these limits. And this could be communication overhead. If you think about that now, you have to communicate with 512 cores in parallel over all your data domains. So communication overhead is often one idea of it, or again, serial gathering parts or so. But in the end, we will see that nobody can really achieve complete linear scaling, especially if you go higher and higher. There will be the, let's say, machine parts kick in, which means basically communication. It's a bigger system. So basically your application uses a whole system. and then the communication overhead will get more substantial, for instance. So thinking of this, you could now think about, it's still nice, but at some point in time, it maybe drifts off too much, where we say, basically the tail off means we lose more and more of the parallel efficiency. So the question is, at some point in time, should I really waste the course if I almost not get any better speed up, right? Because a tail off can be sometimes quite substantial. You see here in the hybrid data set 2, it kicks off quite dramatically. So it suggests that with 1024, I almost get no increase in speed up by doubling still the number of cores and energy I put into the problem. Hence, this is something to study, especially if you think about scalability, scaling it up as we call it. Now, there are different parallelization goals that you can basically see in that context. And this is something where now strong scaling and weak scaling comes in. And this is something where you basically should divide this in your head and think strong scaling is really obvious. It's the intuitive way. You would say the problem stays always the same, right? And you just increase the number of processors. So that's very obvious. You have this one big problem, this one big array, you have this one big galaxy you want to simulate, that one big train, and then you increase the number of processors and you will see how much better you basically can speed up the simulation. You will see that at some point in time, there will be also the tail off, because then the more and more cores you have, the communication kicks in. But still, you can very intuitive say, this is my parallelization benefit. Obviously, basically the train is now simulated instead of half an hour in 10 minutes, something like this. So very clear. What's not so clear from experience talking to students and from exams, this is weak scaling now. And weak scaling, as the name suggests, is a bit interesting. It means a little bit like that we want to do better problems or bigger problems, and basically keeping the work per processor the same. But of course, that means when we have more processors, we need more work, right? I think this is something now what is not so obvious. Here we add to the problem. We're thinking about getting better simulations, more fine granular simulations, more particles, right, for instance, or we want to have the ocean waves much more granular, basically simulated. And this is something where you can think maybe as a tip, go towards reality. So what would be possible? We introduce more work. Although we keep the work per processor the same, the overall problem size will be different, right? And this is a contrast to strong scaling, where the problem size stays always the same. In the weak scaling, I basically add to the problem to keep the processor with the same work. Also, this is, of course, facing lots of limits in practical applications, because at some point in time, you maybe cannot just add to the reality, and then you have your parallelization goal basically also achieve. And let's look at this a bit more when we come to some small formulas. Again, the strong scaling, very intuitive. You have so-called, you would say, for a fixed size problem, right? The time it takes for a fixed size problem is the serial parts of an application. Maybe, for instance, serial part examples are the MPI environment needs to be started up before you actually can do parallelizable parts. That might be a little bit of an overhead, or several communication aspect of distributing your MPI application among many cores and then starting the MPI application properly. So there are a couple of, let's say, serial parts, but you would say the overall time is then the S plus P, the parallelizable part. Obviously, when we have n parallel workers, this parallelizable path, we can basically divide by the factor of n, which means basically with more and more workers, we basically can smaller this parallelizable part, and with this, the overall time for a fixed size problem. And this means, of course, we have the basically a smaller time to solutions. That's what we want, and the overall time is smaller. And this is basically the parallel efficiency that we then have to look on. When you do more of this, chances are that basically the that the processors do almost nothing anymore. And then the question is if you really want to burn the core hours, right? So something to observe that this makes sense. You cannot just to every problem add more n workers. And I think also you will see that in the later parts of the CFD simulation, that there are also, of course, useful limits. And here are some good examples of this tree code where you have now these two plots together, where we see the strong scaling example now. So strong scaling, if you remember, was basically, you see here for each color, a certain number of particles, right? And this means the overall problem of these particles stays the same in all of these color lines, right? In each of these. What we then do for each of these lines, we increase the number of cores, right? So that means the overall problem size stays the same, but we increase the cores, and you see immediately the tail-offs here in parallel efficiency. So where we have to think about, do we really want to add 500,000 cores to the problem? If you see already that basically we have a strong tail-off here. So this is different particle setups, right? That's why we have different colors, and all of them in itself are now these strong scaling. And you see essentially the same here, where you basically have a kind of fixed total problem size, again, with different, scaling plots for all the different number of particles here. And these are basically then the results. And you can see also very interesting tail-offs. So, and basically this reflects to different parts of the application. Just for notation, you would say it's the same. It's not the same. While the particle distribution is quite homogeneous here, you see it is actually a little bit better in the computing, so to speak, not dramatic tail-offs. We see in the inhomogeneous setup. It's a different use case if you want. This is different particle setups. Then you basically see much more quicker these tail-offs, because of course inhomogeneous distribution means, again, you would have, let's say, a domain decomposition, which is not so easy to do than in the homogeneous particle distribution, and there you would have much more work to do. This is now important to understand that this is a strong scaling example. Now come to weak scaling. Now weak scaling is now basically very similar. Of course, you have this kind of variable setup, right? Now variable problem. As I said before, the overall total problem size is the same in basically strong scaling. And weak scaling, we change this because we want to keep each processor busy. That means we add a certain factor here, to put to each of the different cores to be still working on a problem. This sort of a little bit explaining the alpha here, right? So basically, this is something which we also have to explore, and the best way to adding this with more processors, which we can do with N, is also that the problem sizes then needs, of course, proportional to this, basically increase as well to keep the processor busy, right? And that's the idea of weak scaling. So you can have more granularity, whatever the factor is that you basically have there. In one respect, you would say you could have a very nice granular simulation, but what would be then the limit? The memory, right? You cannot maybe do more and more granularity by adding more workers. And in fact, sometimes you see memory bound applications and so on that basically you would have more workers available, but just not more memory. So you actually don't leverage all the cores in the system maybe, but you want to have the whole memory used for a certain problem. Let's look a little bit to the plot, what that means. Again, parallel efficiency looked at from the runtime perspective here, and we see also more tail-offs. Here's now interesting to see that each of these runs, of course, basically reflect to a certain number of particles per core. This is now important, right? It's not the overall number of particles in the whole problem. We talk about keeping each core busy with 10,000 particles. And this is a difference to strong scaling with weak scaling here, right? So we basically keep them still all busy with this number of particles. And you see here with the 140,000 particles per core, the tail-off comes a little bit later because there's still much more to do. And this is actually by almost 500,000 cores, right? So you can imagine the tail off is lots of communication is kicking in, communicating the results of this particular interactions with all this 500,000 almost, right? It's 460,000 almost cores here. So, and this is something where, of course, by giving this number of particles, more and more interactions will happen. And with this, also the runtime is basically then increasing. And at some point in time, and this is now the idea of this weak scaling, is it's also something to see, does it make sense to do, and so on. But of course, it is basically alluding to one of the laws of computer science and HPC particular, which we call Gustafson's law here, which shows basically with weak scaling, we need just bigger problems, right? Larger problems for larger number of CPUs, more granularity, because bigger problems in a way, of course, scale better. There's more things to do. And when you think about there's maybe some serial parts in it, because the overall parallelizable problem is just bigger, the serial parts get almost insignificant. And again, think about that we have here a very varying size of problems, because when I keep here by adding more number of cores, the particles per core constant, the overall problem size will change, while in strong scaling, I kept that actually fixed. And this is, I think, the best to understand. Just another law, because we had Gustafson law, is more related to strong scaling. Also, when you think about now, where are the limits again with the serial parts? And this is well known as Amdahl's law, that no matter what you do, and you see here, this is basically 1 minus S, basically meaning the P, right? The parallelizable part. When we say the overall application is 1, and we have a parallelizable part minus the serial parts is the parallel parts divided by N. So more workers, that's fine. But still the problem remains that the limit in one application here is the serial parts. So no matter how much you do for N, the serial parts in one respect will be never the ones that you can parallelize, and you then of course can also not get a speed up of that. And the scalability, so basically we say in Amdahl's law is basically determined by the serial parts of an application. Hence you want to have this as less as possible, obviously, which means you try to parallelize as much as possible. Hence also the master worker paradigm, right? It's perhaps sometimes not that easy. Or as we also see, the communication overhead or the MPI environment that needs to be set up. There are several, let's say, serial parts of an application, which is not so easy to parallelize. In order to basically understand all of that in detail, you can imagine when I have now 500,000 cores, as I was basically giving you an example of an older machine. Nowadays, we have even more cores available. It's getting out of hands, right? Basically, a human really faces the limits by really understanding the application, the MPI behavior. And hence, there are tools called parallel performance analysis tools in HPC that you can use with HPC applications like using MPI or OpenMP to really analyze and basically tune your application. You see a little bit here how that is working. In this particular CFD special in this course, we will focus on parallel performance analysis a lot, but basically here and there, we will mention it. You see here a system called Scalability, which will be then basically analyzing your problem, which is a performance problem you face, maybe load imbalance because of a late sender. Where is it exactly in the program, in the source code, and where in the system is a problem happening in the topology of the HPC system. And there are other systems like SCORP, Vampire is another one, where you can have the whole communication paradigm of this MPI applications analyzed, and then also get some feedback on your domain decomposition. Do you maybe do another approach? Is a master, let's say, really blocking too much? Do you need more masters to basically control all the different workers? Do we have a bottleneck, for instance, in an IO node, right? We learned in one of the very early lectures, they're not always only compute nodes. Several machines have also IO nodes. Maybe IO is the limit here to introduce parallel IO. So there are different questions where you can actually tackle those performance analysis challenges, but this goes beyond, I think, the idea of today. I just wanted to say here and conclude with this particular slide that it is not at all easy to really scale up a machine. We have now learned the theoretical theory parts of it. What are the limits, like Amdahl's law, for instance, in the serial limits, and you understand a little bit of speed up and so on, but you have also hopefully learned that just by adding more ends and more workers to your problem will be probably not always solving basically the problem of the application. Makes it fast at some point in time, but you will also basically observe then tail-offs in this kind of speed up diagrams. So, so much for lecture 3 today. I hope you learned a lot about these fundamental terms, and some from theory to practice needs to be really considered here when I talk about, you know, the dividable by n part. Always adding more cores and throwing that to a system is not really helping. Here you see a nice example, for instance, where basically the stress on this material in this application is basically around these factors. And if you look the video, you will see the domain decomposition is much more fine granular here, because here's where all the stress, where all the physics have a hard time to compute, while the outer parts here are basically more or less constant or just not moving that much. The main concentration on the material is here, and hence you see also the domain decomposition is much more fine granular here to compute more accurate, to, you know, basically speed up the computation, especially in these areas. But this is something where this totally depends on the application domain problem. This is just one example where HPC used basically on stress of materials when you basically want to maybe build new materials and so on and use them in practice. So please have a look at this video, and we will have much more examples from Reza also in the second part here in the HPC course later. That's all for today with lecture 3. We will continue with lecture 4 next time. See you then.